In this video, we continue our studies of exponential functions of bases other than e. This time, we will graph a function that involves a log base a of x, where a is not equal to e. We'll probably also revisit logarithmic differentiation. There was kind of a cool problem in the textbook that I wanted to go over. And I think that'll probably be it. And then in the next video after that, we'll do some antiderivatives and integrals involving that a to the x. And then in another set of videos, we'll do some of the applications of exponential functions, which are very, very interesting. So for now, let's look at a logarithmic function. Let's try to sketch it. So I've got f of x equals x times log base 4 of this 5 times x plus 1. If I want to sketch the graph, the first thing I need to do is find the domain of the function. Now remember, whenever you're finding the domain of a logarithmic function, whatever's inside that logarithm has to be positive. So the domain of f is the set of all real x values such that 5x plus 1 is positive. And if 5x plus 1 is positive, that means 5x is greater than -1. And if we solve for x by dividing both sides by 5, we get x has to be greater than -1/5, or if you prefer, -0.2. So that is our asymptote. So it doesn't have an asymptote of 0, it has an asymptote of -0.2. Or x equals -1/5 if you prefer. So this is not to scale. And we see that when x equals 0, we have 0 times log base 4 of 5 times 0 plus 1, which is 1. And you say, well, 4 to what power is 1? 4 to the 0th power. So this is just 0 times 0, which is 0. So our function is 0 here. And then typically, as x approaches that asymptote, this expression or the logarithm itself would just go to -infinity. But I'm taking those y values that are approaching -infinity and I'm multiplying by a negative x value in this region. So that negative times a negative, I imagine, is positive. I think this function's probably going to go to positive infinity there. So let's see. I want to take the limit as x approaches -1/5 from the right. So I have x times log base 4 of 5x plus 1. This function goes to -infinity, and this function goes to -1/5. So -1/5 times something that's very large and negative is going to be very large and positive. So we're going to get positive infinity there. And I don't know what the rest of the graph looks like, but I know that that's true. And then as x goes to positive infinity, I know x goes to positive infinity, and the log base 4 of this function of x is going to go to positive infinity as well. So a very large number times a very large number is a very large number. And so I would expect the end behavior of this to be positive infinity. So the graph is going to go up like that on the end. Now what happens in between? That's to be determined by our first and second derivative. So let's compute the derivative of this. Computing the derivative requires us to use the product rule. Got the derivative with respect to x of x times log base 4 of 5x plus 1. And our first function is x. Our second function is this log base 4 of 5x plus 1. So we say, well, we're going to have to take the derivative using the product rule. The derivative of a product is the derivative of the first times the second. Plus the derivative of the second times the first, which in this case is x, undifferentiated. Then you say, okay, I've got log base 4 of 5x plus 1 as my first term. And then the derivative of this piece requires us to use that derivative rule for log base a of x. So remember, we computed this last time. The derivative with respect to x of log base a of x is 1 divided by natural log of a times x. So in this case, our base is 4, so we're gonna have a natural log of 4 in that denominator. And we don't just have an x inside, we've got a 5x plus 1. So we're gonna have to use the chain rule, where 5x plus 1 is our inside function. So we have the derivative of log base 4 of this inside function is 1 divided by log, or the natural log of 4 times the inside function times the derivative of the inside by the chain rule. The derivative of 5x plus 1 is just a 5. And you're multiplying that by an x. And I wrote that in the numerator so I could have a 1 in the denominator. If I multiply straight across, got log base 4 of 5x plus 1 plus 5x divided by natural log of 4, which is just some positive constant. It's going to be greater than 1 because e to a number that's greater than 1 is going to equal 4. E to the first would be that 2.7 inside, so we've got this. And that's our derivative. And then if we want to determine any critical values of this function, we would have to set this expression equal to 0. Ooh, okay. Well, I guess we could get a, should we get a common denominator? Oh, I think it's going to get really bad. I actually don't know when this would equal 0. So this is actually a problem where maybe I should use my graphing calculator to find the zeros of this function. Well, actually, let's try it. Let's set this equal to 0 and solve for x. Well, in order to do that, I'm going to subtract this term from both sides. So my log base 4 of x is negative 5x divided by natural log of 4 times 5x plus 1. And I need to get rid of that log base 4 of this side. So I might exponentiate. Oh my goodness. So 4 to this power equals 4 to that power. So I end up with 5x plus 1 on the left equals, well, that expression. Oh goodness. I have no idea when that's going to be true. So if I want to find the zeros of this function, I think it is best to use a graphing calculator because we've got an exponential and we've got a polynomial and we need them to be 0 at the same time. But in the exponential expression, we've got a rational function, got a polynomial in x divided by a polynomial in x. And then we've got that extra natural log of 4 in the denominator. I can see from this that as x goes to infinity, we end up with this term has a horizontal asymptote of 1 divided by natural log of 4. Because this 5x and the 5x plus 1 are very similar. As x goes to infinity, it's going to approach 1. If x is really large, that plus 1 doesn't matter very much. So we end up with 5x divided by 5x, which is getting very, very close to 1. It's always going to be a little bit less than 1 because of that plus 1. This divided by this is always smaller than 1, but it's going to get very, very, very close to 1. But then we multiply by that 1 divided by natural log of 4 there. And you say, okay, that's what we've got going on here. And you say, well, what happens to this? Well, I mean, again, is end behavior even appropriate here? No, we're just trying to figure out where the derivative is 0. So I think the best way to find the x values where the derivative is 0 here in this case is to use a graphing calculator. So we would graph this function and then find out where it's 0. And then we can look at the graph to determine the signs of f prime to the left and right of this function. Okay, so that's the plan. And then if we want to take the second derivative, take the derivative of this piece. So the derivative of log base a of some function is 1 divided by log base a, or natural log of a, excuse me. So natural log of 4 in this case, times that function, which is 5x plus 1, times the derivative of the inside by the chain rule, which is a 5. That's the derivative of that piece. And then the derivative of this requires a quotient rule. So we'll have the bottom function times the derivative of the top function, which is 5. That's low d high minus high d low. the derivative of 5 natural log of 4 times x is 5 natural log of 4x. Well, the derivative of 5 natural log of 4 times x is just the 5 natural log of 4, excuse me. The derivative of a constant times x is just the constant. And the derivative of 1 times natural log of 4 is just the derivative of a constant, which is 0. So we've got that, all divided by low, that denominator squared. So we end up with 5 divided by natural log of 4 times 5x plus 1. And then here, if we distribute this 5 times the 5x times the natural log of 4, well, it's actually only distributed once. 5 times the 5x is going to give us a 25x times the natural log of 4. That's going to cancel with this one. So this guy cancels with that. And we just end up with a 5 natural log of 4 in that numerator. You say, okay, well, one of the natural logs of 4 will reduce. And now these denominators are almost identical, but this one is missing an extra 5x plus 1 factor. This one's got that 5x plus 1 squared. So we'll multiply the numerator by 5x plus 1. That's cool as long as we do the same thing in the denominator. Now, if we add the numerators, we've got 25x plus 5 plus 5, so that's plus 10, all divided by natural log of 4, which is just a constant, times 5x plus 1. So that is our second derivative. That one I can actually solve. We can find out when that's 0. Factor out of 5 from that numerator. We have 5 times 5x is 25x. 5 times 2 is that 10. And of course, we're only interested in this when x is greater than that negative 1/5, so that our logarithm is well defined. So f double prime is undefined at negative 1/5, but that's an asymptote of the original function. That's our domain. Negative 1/5 to infinity. We say, okay, well, when is f double prime equal to 0? F double prime is 0 when the numerator is 0 and the denominator is non-zero. So we'll have 5x plus 2 equals 0, or 5x equals negative 2, or x equals negative 2/5. Well, that's actually to the left of this. X equals negative 2/5 is not even in the domain of the original function. Not in the domain of f. So it looks like our function has no points of inflection. So say, okay, to the right of negative 1/5, what is the sign of 5x plus 2? Well, if 5x plus 1 is positive, then 5x plus 2 is definitely positive. Positive times a positive divided by a positive times a positive. So this is going to be positive all the time. So if it's positive all the time, that means the graph is always concave upward. You say, okay, I know it's concave upward for all x values in the domain from negative 1/5 to infinity. And then it will probably, if it's concave upward the whole time, and there's potentially an x value where this equals 0, that x value is probably going to switch from concave down, or from decreasing to increasing, so that we'd have a relative min because it's concave upward, right? But I don't know how to solve that equation because I've got this logarithm and this rational function, and it's really hard to get x by itself when you've got a logarithm and a rational function. In order to get rid of that logarithm, I had to exponentiate, and then I end up with a polynomial and an exponential, and those are really hard to solve. And we've got the rational function inside the exponential now, so it seems to get worse and worse. But we can solve this, or we can estimate, and I think it's probably just going to be 1, 0 of f prime using Desmos. So we'll graph the function, and then by looking at the graph, we'll be able to infer relative extrema. And again, because the function is concave upward all the time, I'm expecting a relative min. I'm expecting it to be decreasing and then increasing. And then at some x value, it's going to switch from, the original function is going to switch from decreasing to increasing, and that's where we'll have our relative min. So using my graph of f double prime, this is what I'm expecting. Negative 1/5 to infinity. There's some x value here where this equals 0. I don't know what it is. I'm just going to call it x naught. And then I expect it to be negative on this side, or f prime to be negative on that side and positive on that side. So the function goes from decreasing to having a 0 slope to increasing. And so we'll have a relative min at that x value. But to find that x value, we're going to use Desmos. All right, that's the plan. Let's go to Desmos and see what this graph looks like. And actually, that's what I see as well. As x goes to negative 1/5 from the right, we see that the function goes to infinity. We said as x goes to infinity, the function value goes to infinity. So it looks like I'm expecting a relative min. And I also expect it to be concave upward. So things look good here. I just wonder where that minimum value actually is. So to do that, we'll go to Desmos and graph. Let's look at the derivative first. And then once we graph the derivative, I'm trying to have a little mystery. I don't want to graph the original function first. I want to try to get some sense of the original function by using the derivative itself. All right. So our derivative is log base 4 of 5x plus 1 plus 5x divided by natural log of 4, which is just a constant, times 5x plus 1. And we said we had an asymptote of x equals negative 1/5 or 0.2. This sort of looks like a logarithmic function, doesn't it? Looks like we're taking this logarithm and then we're adding something that is close to 1 divided by natural log of 4. What is 1 divided by natural log of 4? That's about 0.72. Say, okay. That's what our graph looks like. Wait a minute. Did I do that correctly? Oh, that's the graph of f prime. The graph of f prime. So I said, is there any x value where f prime is equal to 0? And yeah, there is. Oh, it looks like at x equals 0, we get 0? Oh, that's true. F prime of 0 is log base 4 of 1. So you say 4 to what power is 1? 0. Plus 5 times 0 divided by natural log of 4. So you just get 0. I mean, if you want to, you can type natural log of 4 and then 0 plus 1. So you've got 0 divided by a constant, a non-zero constant, so you get 0. All right, so our extrema of the original function must lie at x equals 0. So if I want to, I can evaluate the original function there. The original function was f of x equals x times log base 4 of 5x plus 1. And I don't want to graph it. Try not to graph it. 5x plus 1. Now I want to evaluate that at 0. So I have, oh, actually we've already done this. So we have 0 times natural log of 1, which is 0 times 0, which gives us a 0. So the function value is 0 there. So I think that's our relative minimum. You say, okay, well, how do I know it's a relative minimum and not a relative maximum? Well, let's focus on this graph of the first derivative. So that's what we've got here. And I want to look at it close to 0. So I want my x's to go between, let's say, negative 0.2. Oh, actually, that's where our asymptote is. Let's go to negative 0.5. Let's go to negative 1 at least. And then we'll let our x go all the way out to 2. So locally, it looks like this. So our derivative is 0 at x equals 0, and then it's negative on this side and positive on this side. What does that mean? Well, that just means that, well, it actually, we could have inferred that, couldn't we? No, actually, it's not necessarily obvious. Well, actually, maybe it was. Anyway, just reading the graph now, we see that the y values on the derivative are negative. So what does that tell us? That means the original function is decreasing. The original function is decreasing until we get to 0. And then at 0, it turns around. and it goes off to infinity. And then the function's second derivative is positive all the time. So it's concave upward. So what I'm expecting, let's see, is the following. Trying to get my camera right. For some reason, it's not giving me the option to view my document camera. Okay. All right, so there's something going on with my document camera. I don't actually know what it is. I wanted to graph the function on paper for you. So I think what I'll do is I'll just hold up my paper for a second. It's unfortunate, but it is what it is. Gotta love technology, right? So we're gonna have a function that is concave upward the entire time. It's decreasing until you get to 0, and then it's increasing from 0 to infinity. So I'm gonna say roughly, it's gonna look like that. I don't know, is it reflected? Is it flipped? So we've got that, whoops, vertical asymptote right there. Hard to do. It's very weird. Vertical asymptote there. And then it's concave upward, and then the behavior near the asymptote, the function goes to infinity. As x goes to infinity, the function goes to infinity. It's concave upward the whole time, and then it's concave, or it's decreasing on this interval, and then it's increasing on this interval. So what you guys see? I hope so. So now let's graph it on Desmos. And that's our original function. All right, so here's the derivative. And the original function looks like this. And we can see that if we plot that point at 0, 0, the function's decreasing until we get to 0, 0, then it's increasing to the right of 0, 0. The graph is concave upward the whole time. Yeah, I think that that's it. So that's what our function looks like. It's not particularly interesting. And then as x approaches a negative 1/5 from the right, the function goes to infinity. As x goes to positive infinity, the function goes to infinity as well. It looks like it's not graphing it very far. It's only going up to this point. But I believe it would continue. Most of the time it would continue. I don't know why it's not continuing. I would expect that would continue all the way to infinity. Yeah, at x equals negative 0.2, it just says undefined. Okay. All right, but that's the idea. The function should continue. It should be getting infinitely close, or not infinitely close, should be getting arbitrarily close to x equals negative 0.2, which is that vertical asymptote. All right, and I've got some more calculations to do, but I think I'm just gonna go to a new location. Might have to get a new adapter for my document camera. But I'll make some more videos for you there, and we'll continue our calculations. I guess that's it for that. We'll do some logarithmic differentiation in the next video. We'll do some antiderivatives and integrals involving functions of the form a to the x or a to the f of x. See you next time.